Thanks everyone so much for coming. This is the start of the HDX workshop. We'll have 3 days of different speakers. I'll briefly overview sort of what's going to happen in a couple of minutes. So let's go ahead and get started. This is the intro talk. It's eventually going to be about high-dimensional expanders and a corresponding powerful set of tools developed in the literature called the local-to-global method. I want to start a little bit zoomed back and talk briefly about sort of the local-to-global phenomenon in TCS at large, and highlight a few places where high-dimensional expanders have recently fit into the picture. And then we'll actually go into details on setting up notation definitions, etc., and some main results of the area for the rest of the workshop. And feel free to stop me throughout if definitions are unclear or anything like this. If we don't get all the way through the end, it's not critical for the rest of the workshop. Making sure we understand the basic definitions is fairly critical for the rest of the workshop, so please stop me early on rather than waiting. Let's go ahead. So like I said, I want to start with sort of some highlights of the local-to-global phenomenon in TCS and where HDX fit. And if you are already familiar with the Stock 2025 program, you might know where I'm going to start, which is the problem of the PCP theorem, probabilistically checkable proofs, which we've just seen a major advance on in this conference, or we'll see in a couple hours. So if you've never heard of PCPs before, this is fine. Let me explain sort of the very basic high-level idea. This is not a talk on PCPs, but let me explain for 2 minutes or something like this. So hopefully everybody remembers the class NP. It's a fairly important class. Right? This is the class of languages that is membership is verifiable in polynomial time. So roughly speaking, looking up here, recall that a language is in NP if there's a polynomial time verifier. Think of yourself as being the verifier. Such that given there's a polynomial time verifier V, which reads sort of the input, which you think of as like a possible 3-sat formula or something like this. And if X is in the language, there must exist a proof or witness that somebody can give you that convinces you 100% of the time that that instance is in the language. Right? For 3-sat, this is like a satisfying assignment or colorable coloring of a graph or something like this. On the other hand, if X is language, none of these witnesses is going to convince you that it isn't language. You can read the whole proof, right? Some polynomial size proof, and you'll find an error eventually, right? Somewhere in this proof. You can't be fooled. The PCP theorem is a cornerstone of modern complexity. It was shown in the 90s that there's this incredible alternate local characterization of NP, which says, to me, this sort of very surprising statement that there's a way to encode this witness as a proof pi, sort of possibly longer encoding of the witness, such that a verifier can actually just toss a few coins and read, maybe 3 or 4 words in this large proof and be confident with very high probability whether the input X is in the language or not. So there's some encoding of your 3 colorable graphs, just that I check just a few locations, and I'll be very sure whether you sort of given me a valid 3 coloring or not. So this was proved in the 90s. I'm sure many of you are aware it has implications, not just in complexity. A lot of cryptography, interactive proofs, and things like this have stemmed from research in PCPs. Hardness of approximation is entirely based upon this material. It's an incredibly important piece of complexity in theoretical computer science. So given this fact, a major question in the past 30 or so years in TCS has been what sort of structures, sorry, we're going to miss some slight words on the top right. It says behavior. What sort of structures give rise to this type of local-to-global behavior? How can I encode my witness in this way where I can just locally check, at random, 2 or 3 words in this 100-page proof that you've given me, and yet I can be very confident that I'll reject something that's not in the language with high probability? Okay, so originally this was done via low-degree polynomials. I'm going to be very high level here. Of course, I'm leaving out, many, many, many things. Roughly speaking, this was originally done with low-degree polynomials testing. It was famously observed by Ron Raz that you can sort of repeat a problem a number of times. This is sort of akin to using a complete hypergraph to amplify success. This is parallel repetition. And of course, famously, Eric Deneur reproved the PCP theorem, somewhat better parameters, using just expander graphs. A fairly incredible work. Unfortunately, all of these methods classically hit various barriers. There are a number of parameters in PCPs. I'm not going to bore you by going through all the different parameters and what the different methods get you. You might hear some about this more in later talks that are actually about PCPs. not just an intro to the HDX workshop. But believe me when I say that all of these methods hit various barriers in trying to construct optimal probabilistically checkable proofs in hardness of approximation. And this led to a beautiful idea of Kaufman and Mass and Denner and Kaufman, building on a number of earlier works in the area. If we can use these ideas of expander graphs, which are sort of sparse models for the complete graph, sparse graphs that mimic the properties of the complete graph. We'll talk about them more in a bit. And we can use the complete hypergraph. Is there some way to push further, to push beyond these barriers by using some sort of analog sparsification of the complete hypergraph, sort of in place of what the parallel repetition theorem and what Ron Rouse does? If this doesn't mean anything to you, it's fine. It's not critical for the rest of the talk, but somehow there's a natural idea here to try to use sparsifications of the complete hypergraph that we'll be calling the class of high-dimensional expanders. So this talk, building on sort of 20 years of work on this direction, we learned the answer is yes. This work of Bofna, Minzer, Voss, and Yoon breaks a long-standing barrier in PCP efficiency and uses high-dimensional expanders to build an incredible new family of probabilistically checkable proofs. So Mitali will talk more about this, both in the best paper session today and in day 3 of the workshop. She'll talk more about the underlying HDX machinery and sort of local to global tools that go into this result. Okay. Maybe you don't care about PCPs at all. Maybe you care about Markov chains. Let's talk about something completely different. Maybe you're an algorithms person. You don't care about PCPs. So here's a different concrete problem. Say that I give you a graph, and I ask you to give me a random spanning tree of that graph. Or maybe I want you to give me a random independent set, or a Q coloring, or something like this, some type of combinatorial structure of the graph. Notice that naively, a graph probably has exponentially many spanning trees. Right? So it's not so obvious how, in polynomial time, you're going to sample for me even approximately a random spanning tree. Okay, I'm sure many of you know there are algorithms to do this, but these types of combinatorial objects, it's often difficult to sample. So what's a classical method of doing this? We'll use some sort of randomized local dynamics, corresponding to something called a Markov chain. Let me just give a very concrete example for spanning trees. I'll do sort of the following 2-step process. Let's say I first find some deterministic fixed spanning tree T to start with. This is not hard. I'll now apply again and again the following local updates. I'll apply a down step. So let's just look at the picture. I'll start with a spanning tree. Let's say this is of K4. I'll start by removing one of the edges at random. Right? Here I've removed the left edge. And then I'll add back an edge, what I'm calling the up step, to get a new spanning tree. So I add back a random edge, conditional on it creating a new spanning tree. So okay, this is some local dynamics. I've started at a deterministic place. There's a natural question. Does this converge? Does this process converge in polynomial time to a nearly random spanning tree? How many times do I have to repeat this single, very local update to get a sort of near global uniform distribution here over spanning trees? As they're exponentially many, it's not clear a priori that I can do this in polynomial time. It might be I have to run it exponentially many times, and then it's sort of useless. So today, a lot of the focus will be on developing tools in spectral high-dimensional expanders and the local to global method to actually show that this indeed mixes very, very quickly. I guess you can probably get n log n. We're only going to show n squared or something like this, but we'll show sort of a low polynomial mixing time for this, as well as many, many related chains like on independent sets and things like this. Jonathan will talk about lots of extensions of this result and very interesting connections with geometry of polynomials. Okay. Let me just zoom out one more time before going into details on expanders and HDX. I've just sort of snapshotted 2 fairly famous examples of local to global structure. And of course, I've picked ones in which HDX are already known to be very effective use. There are a huge number of uses of local to global structure in TCS, right? Local algorithms, optimization, things like SGD, right? Making local updates to get to a global optimum. Property testing and pseudo-randomness. We'll hear from Rachel on day 2 some applications of HDX as well. TCS is full of this type of local to global phenomenon. And largely the point of this workshop is hopefully to get a high level idea of what we know so far about where HDX fit into the picture. And for the audience to keep in mind, can we use this type of machinery in your subfield? Likely there is some type of local to global behavior in things you study. Can we somehow use HDX here? We have 4 or 5 examples where HDX have been incredibly powerful. I'm sure there are many more, and it would be great to have people's expertise to sort of see where this should fit into the broader picture of TCS. Okay, briefly a workshop overview. I won't actually say that much because you can just look at the website. But roughly speaking, every day we've sort of structured it. So there's like some development of tools and machinery. Today is sort of spectral HDX and basic local to global ideas. The next day is constructions, and then we'll talk about combinatorial type expansion instead of spectral on the last day. And we'll see, each day we'll also see applications in theory. Today, Markov chains, approximate sampling. We'll see these nice constructions, recent breakthrough on lossless expanders. And finally, the last day on PCPs and quantum codes and complexity. Okay. Great. And I mean, that was fairly high level, but are there any questions before we move to the actual technical material in the talk? Maybe somebody make up a question so I can drink some water. Okay. Great. So yeah, things will now become slightly more technical. So please, again, stop me if a definition is unclear, and we can spend a little bit of time on it. Okay, so I'm sure that most of us already, I'm going to move this down here so we can see, already know and love expander graphs. Expanders are, roughly speaking, sparse, robustly connected graphs or networks, like the one shown here, that mimic the complete graph Kn in various different ways. They are ubiquitous tools throughout theoretical computer science. I think it's probably easier to find, it's hard to find an area that they have not had some sort of seminal or breakthrough application. And I've listed a couple here in complexity, encoding, and algorithms. I could go on, networks, et cetera. They're incredibly powerful and flexible objects. Roughly speaking, I sort of mentioned, alluded to this earlier, there's sort of two types of expanders, or definitions of expansion. There's combinatorial expansion, which is maybe a little bit more physical and natural. And there's spectral expansion, which we'll talk about. It has to do with the eigenvalues of the adjacency operator of the graph that you're working on. So I'll just very briefly talk about combinatorial expansion to give you some feeling for it before we sort of drop the notion and come back to it day 2 and 3 a little bit. Roughly speaking, combinatorial expansion says something along the lines of all small enough subsets of vertices in your graph expand outward. There are many variants of this definition. They're all roughly connected to each other, but not, they're not exactly quantitatively equivalent. And we'll talk a little bit more, say, on day 2, how hard it is to construct like lossless vertex expanders or various things like this. But roughly speaking, just think of the picture for now, right? Subsets expand outwards. Maybe they have many edges going outwards. Maybe they have large vertex neighborhoods. They're all different definitions, but they're all sort of the same rough flavor. I'll mention one in particular, which is probably the most famous, of Cheeger's constant. It doesn't matter too much at the moment to understand this. This is just measuring the number of edges. This is sort of the worst case number of edges going from S to the rest of the graph, normalized by its size. So this is sort of like a bottleneck ratio. It's saying if this constant is large, there are no sparse cuts in the graph. There's no way to cut things so that there are very few edges going between two large portions. Okay, so we'll return to this in a couple days, but mostly that's all I'll say about that. So let's go ahead and move to sort of the protagonist of today's talk, which is spectral expansion and eventually generalizing this to high dimensions, to hypergraphs. So I know all of you know what the adjacency matrix is, et cetera, but let me just make sure that everybody's on the same page, and I set up notation and things like this. So given a graph G with vertices V and edges E, I'm going to assume things are regular throughout this talk for the most part. It's not actually true. I'll sort of mention when things aren't going to be regular, and maybe I'll briefly mention how you would adapt things. But for simplicity, for a 1-hour overview talk, everything's regular, and we're not going to worry about sort of irregularities and various things. But all the theory extends very naturally. It's easy to do, and if you look up lecture notes online, you'll see the extended irregular weighted theory. Okay, so the normalized adjacency matrix of G, at entrance VW just has 1 over degree if it's an edge in the graph, and 0 otherwise. Right? It's just encoding linear algebraically the structure of the graph. This is of course a symmetric and doubly stochastic operator, and so it has an eigen decomposition, and in particular it has n eigenvalues, where n is the number of vertices, going from 1 to -1. Because things are stochastic, there's always an eigenvalue equal to 1, which corresponds to the all ones vector, sort of the trivial eigenspace. a graph is called a spectral expander if all of the non-trivial eigenvalues, lambda 2 through lambda n, are small. There are generally two variants of this. There's one-sided spectral expansion, which just tells you that lambda 2 is small. And there's two-sided spectral expansion, which tells you that both lambda 2 and the absolute value of this negative 1 over here, this smallest negative eigenvalue, are both small. We'll mostly focus on one-sided expansion throughout, except in a couple of places. And finally, I'll note sort of what does this have to do with this sort of combinatorial expansion that I talked about before. I'm not going to go deeply into it, but it turns out that this Cheeger constant that I defined, this bottleneck ratio that I defined on the last slide, lambda 2 is sort of like an analytic relaxation of this value. It optimizes over real valued functions instead of 0, 1 valued functions. And they're related quadratically to each other. So often spectral expansion is thought of as sort of a rough approximation for this nice combinatorial expansion behavior that's hard to actually compute. Or rather, lambda 2 is an easy version of this to compute. OK. But I really want to claim that spectral expansion really has a life of its own, right? It's not just an analytic relaxation of combinatorial expansion in graphs. It's its own natural and extremely useful tool. And I want to give sort of two views of spectral expansion that we'll keep in mind throughout the rest of this talk and when we generalize the notion of expansion beyond graphs. The first thing that I want to claim is that expansion can sort of be viewed as a notion of independence, or what I'm going to call pseudo-independence throughout. What do I mean by this? Let's say we're given a graph G on, I'm just always going to have the vertex set be the numbers 1 through n throughout the rest of this talk. So I'll always use n and some edge set E. We can think of this edge set E as a two-dimensional distribution, x1, x2, supported on pairs n choose 2. How? I'm just drawing a random edge, right? And that's giving me a draw from this from x1, x2. It's a random pair coming from this graph. How do we think about independence? Well, in this model, it's not hard to see that the variables x1 and x2, this joint distribution generated by edges, are independent up to self loops if and only if this graph is complete. Right? This is saying that for any particular value of x1, I should have all possible values of x2 remaining. What does that mean in this picture? It means I have all possible edges left, right? And that means I'm the complete graph. So here, sort of independence is the same as being complete, same as being KN. We think of expanders as being sort of sparse models or a sparsification of the complete graph. It turns out that a graph is a spectral expander. I won't, give exactly the formula, but if and only if these variables act approximately independently. In what sense? In the following way, that if I take any two functions f and g of the vertices, here are numbers 1 through n, then the joint expectation across an edge, across this distribution of f times g, is roughly equivalent up to some spectral error to the product of the expectations, the expectation of f times expectation of g. In many applications, this is really the only sort of property you need of independence. And in these cases, we can use spectral expanders as a sparsification instead of the complete graph. This is an incredibly, incredibly useful tool. It's very simple, but very powerful. OK. The second view I want to give of things relates to the underlying random walk on G and mixing time. Any questions before I move on? Something about what the spectral error would look like. Yeah, so I'm cheating here a little in that this equality really would be the two-sided case. And it will, if you're a lambda spectral expander, it would be plus lambda times the square root of the variance of f times the variance of g. So really say like these are bounded variance functions, then there would be a plus lambda. If you were one-sided, this would be less than or equal to instead of equal. Yeah, I've been very high level here. Yeah, good question. So usually you think about it, you lose, you somehow lose a norm because you move to squared, but it's a little bit in the weeds. It is important, but. OK, so let's now move to this second view, which is also going to be a main focus of the talk. How am I doing on time? So one thing that hopefully everybody knows is that this underlying adjacency matrix AG is the transition matrix of G's underlying random walk. Right? What is this process? This is when I started a vertex and I moved to a uniformly random neighbor. Right? This is given just by multiplying by the adjacency matrix, which has 1 over degree in each of the positions that it has an edge. Right? So this sort of random process, this Markov chain, is controlled by the adjacency operator. The mixing time of G, or of the underlying random walk, is the number of times I have to apply this procedure, the minimum number of steps, such that starting from an arbitrary worst case position or distribution, that after t steps, I will be nearly spread uniformly throughout the graph. If this weren't a regular graph, I would put what's called the stationary distribution here. Let's not worry about it. Things will converge to uniform over the vertices because everything is regular. But it's the minimum number of steps such that I'll get epsilon close to a random output. So hopefully this is linking back to this question about spanning trees and this sort of chain that I defined on them before. That was really a question about what's the mixing time of this Markov chain. It turns out that, coarsely speaking, lambda 2, this sort of one-sided spectral expansion parameter, controls the mixing time of the underlying graph. I'm lying a little bit. It really controls the lazy mixing time so that we can not depend on this negative eigenvalue, -1. I'm not going to focus on this too much. The lazy walk is basically I stay in place with half probability and I move to a random edge with half probability. It'll come back later, so I did want to mention it. But lambda 2, essentially up to a log factor in the number of vertices, controls the mixing time of the graph. So this is another very powerful way to think of spectral expansion. And again, you can sort of feel this is related to no bottlenecks and this type of combinatorial expansion we described before, right? You should sort of only mix if there are no bottlenecks. But here, hopefully, this is fairly clear roughly why this is true, right? Because what does this distribution look like? I'm hitting it constantly with AG. There's one term, which is the all ones, that has eigenvalue 1, and it's surviving every time that I hit this. And every other term is dying by at least a factor of lambda 2. Right, so this is roughly why this is upper bounded. I won't talk about the lower bound, but this is roughly why lambda 2 controls the mixing time of the random walk. Okay. So now I want to move to defining expansion in high dimensions. There are a number of different generalizations that we could look at in terms of what type of high-dimensional structure we're actually interested in generalizing to. It turns out there are many generalizations of graphs that are interesting, and we'll talk about several in this workshop. Today, we're just going to talk about the simplest case, which are uniform hypergraphs. Right? So a k-uniform hypergraph is just a subset of n choose k. Right? If k were 2, this would just technically this is just the edge set of the graph, but it's just now edges have k vertices in them instead of 2 vertices in them. Okay, it turns out, and we'll see soon why, that in the context of high-dimensional expansion, it's extremely useful not to consider just the hypergraph, but the hypergraph and all of its downward closed edges, which is something called the corresponding simplicial complex, or pure simplicial complex. So the complex corresponding to H, xh, is the union of sort of these levels x0 through xk, where xk is just the original hypergraph itself. It's all the k-size sets. x0 is the empty set. And xi is all possible I edges that appear in some hyperedge in the original complex. And probably easier to see a diagram. A very useful way to draw this out is this sort of poset diagram called the Hasse diagram, where I draw the top level edges, and then I just 1, 2, 3 includes 1, 2, 1, 3, and 2, 3, and I sort of draw edges by inclusion in this diagram. This gives me sort of the diagram for the simplicial complex. Let me note here that I am sort of making a mortal sin here, if you're a mathematician, which is that I've written sets of size 3 as x3, whereas if you look in topology or geometry, this should really be x2, because these are triangles, and triangles are 2-dimensional objects. They're not 3-dimensional objects. Unfortunately, this talk is mostly combinatorial and probabilistic, and it's a lot easier to use this notation where this corresponds to set size rather than sort of dimension. Nevertheless, I'm going to call this a k-dimensional simplicial complex, hoping that Alex doesn't watch these. So hopefully that's not too confusing to people in the audience. If you look in the literature, often there will be this off by 1 difference. Usually the papers will specify whether they're using size I or size I plus 1. So I'll use size I throughout. So I want to also sort of talk about the distributional view. Right? Just like we thought about edges and graphs as a 2-dimensional distribution, of course, we can naturally think of each of these levels xi as an I-dimensional distribution, right? As an I-dimensional variable x1 through xi, supported over n choose I. How is this generated? Just like before, I'll draw a random hyperedge. And now there are more levels. So to generate xi, I'll randomly subsample I of the vertices. So this gives me a distribution over all the different levels of the complex. Right? The top one is just, think about the top one as being uniform over hyperedges. Usually it is. Although I think Jonathan will talk about some cases where it's not uniform. And then we downward close by this basic subsampling procedure. So one thing that I'll note is that by assuming things, later on, I'm going to sort of assume that these distributions are uniform. That's a lie. Like in most simplicial complexes that we care about, when you look at this, generated distribution, it will not be uniform. But everything that I say, assuming uniformity, it will all generalize very, very naturally to when you have actual weights in this complex. And I'm not going to worry about it for this 1 hour overview talk. There's one more thing I want to mention in this diagram, which is that if we cut everything off above x2, if we just look at the set of edges and vertices of this complex, we get its corresponding base graph. Right? This is the complete complex. So you can see its base graph has vertices 1, 2, 3, and 4, and it has every possible edge. So here the base graph is K4, encoding the fact that every possible pair of elements appear together in a hyperedge. So you can think of this base graph, the weights of the edges, as capturing the correlation between, say, vertices 1 and 2. How often do they appear together in a hyperedge? So this base graph captures pairwise correlations in the hypergraph. And also just geometrically, is the graph that you would see when looking at this hypergraph if you projected down to edges. OK. Any questions about this definitional setup? I haven't told you yet what it would mean for this to be expanding. That's the next thing. OK. So when should we call a simplicial complex a high-dimensional expander? I'm going to give you a definition here, and then I'm going to motivate it the next slide. So give me, allow me a minute to try to just explain the definition as clearly as possible, and then we'll talk about why it's a natural and useful definition. The first thing I hope everybody agrees is pretty natural. There's this base graph of the complex. We should require that X's base graph is a lambda expander. Right? If we're going to call something a lambda, what's called local spectral HDX, the first thing I'll require is the base graph is a lambda expander. But this in general will not be strong enough for a lot of the things that we're interested in. What we'll actually require is this not only holds at sort of the base level, but it holds locally within every what I'll call a restriction or formally link of the hypergraph X, which I'll describe formally here. So the link, given any face S and Xi, any I set that appears in the complex, the link of S is basically its local view or local neighborhood in the hypergraph. It's a corresponding k minus I dimensional complex that generalizes neighborhoods in graphs, where to define XS, I look at all of the subsets in my complex that contain S, and then I remove S. Easier seen through a picture. Again, it's not like it's that complicated, but let's say we were looking at the link of 1. Right, so the first thing I do over here is I highlight everything that contains 1 and ignore everything else. This is sort of all the faces that 1 sees. Then to make this a corresponding simplicial complex, I need to remove 1. Right, so this now lowers the dimension to 1. Before I had sort of a 3-dimensional size 3 object. Now it's down to a graph. In this case, the vertex 1 saw neighbors 2, 3, and 4. So those are the vertices of this link. And it has all possible edges. So this is just a copy of K3. So all the 1 links in this complete hypergraph are just copies of the complete graph, K3. OK. I also want to give sort of a distributional view of these links, which is very, very useful in practice when you're actually working with them. Which is that these are basically just conditional distributions. Like, what am I doing? So remember, we had this view of the k hyperedges as a k-dimensional variable. All that I'm doing is saying condition on this variable containing S. Right? Say that morally, like the first I values in here give me the face S. That's sort of this first step right here. Look at everything that contains S. And then I'll marginalize. I'll look at the remaining, I've fixed these guys to be S. Now I'll look at the distribution over the remaining variables. That's removing 1 in this process. So these links are really conditional, local conditionings throughout the complex. This will be extremely useful because it will allow us to sort of break global quantities and functions up into local expectations across the complex. And this is sort of the core of local spectral high-dimensional expansion. OK, so now I can actually tell you a definition. I'll move this again so that it's not in the way. This is the beautiful definition due sort of originally to Kaufman, Koch, and Lubatsky in some variants, and the variant that I'm presenting here to Oppenheim. So we'll call X a lambda high-dimensional expander, a local spectral expander, if the base graph of every link is a lambda spectral expander. Note that the link of the empty set here is the base graph. So this includes both the base graph and all of its local, all the local links, base graphs of links. Notice I haven't written one-sided or two-sided here. There are 2 variants of HDX defined analogously. Right? If everything's a one-sided expander, it's a one-sided HDX. If everything's a two-sided expander, it's a two-sided HDX. There are some distinctions in what properties these objects have. I'm not going to go into them in this talk. I'm basically just going to use one-sided expansion throughout. Anytime I write lambda HDX or expander, I mean one-sided. I'm happy to talk with anyone afterwards if they are curious what the differences is between one-sided and two-sided high-dimensional expansion, but it's a little bit too much in the weeds for this talk. Okay, I'll pause again since this is sort of the core definition. If you forget everything other than this, that's not great, but it's okay. It's okay. So let's make sure that we understand this definition before we move on. Any questions? Yeah.
So I mean, does it like you get anything useful or relations if you just require links of certain dimension?
Yeah, so we'll talk about this. In fact, there's a beautiful theorem due to Oppenheim that says if I just have expansion in these top level links, fix everything except two. It's called the trickle-down theorem. This expansion, I'll even give a very high-level proof of this at the end, time willing. The expansion trickles all the way down to the base graph. You sort of just need strong enough expansion at the top level. It'll imply expansion for everything. But you need it at the top. It's
fix everything except.
Yeah, fix everybody except with. Hold on. Right, if I have these variables, fix everything except xk minus 1 and xk, yeah. That gives me a local graph, right? All the different possible fixings of this. If all of these are strong enough expanders, the entire thing will be a local spectral HDX. I'll state the theorem formally in maybe 15 minutes. And in fact, this will be a big topic in the next talk as well. This is a really powerful theorem. It's not true the other way, but you can't start down and sort of move up. Things trickle down, not up. Yeah, okay, good question. Let's go ahead and move on since some of these we will cover. So now I didn't motivate this definition for you. It's certainly a definition, right? If we look back, certainly this generalizes standard graph expansion, right? If I just had a graph, all I would have is the base graph, and this definition would just require it's an expander. So clearly it is a generalization of spectral expansion. The question is it a natural one? Is it a useful one? How do we use it? What do we use it for? Let me give a very brief high-level overview of this. One, in my opinion, very nice way to think about this definition is as extending this pseudo-independence viewpoint of expanders I talked about before. That morally speaking, a graph is a lambda HDX if the k variables, x1 through xk, instead of just x1, x2, again, act sort of pseudo-independent, act independent in a similar way. How does this correspond to this definition that I've given you? So the first one, I sort of already mentioned how the base graph is capturing correlations in the complex, right? The weight of an edge VW is telling you how many times do V and W appear together in the hypergraph. So this is capturing correlations, and saying this graph is an expander is telling me that I sort of have bounded pairwise correlations. It's basically a notion of approximate pairwise independence of these k variables. And the second, link expansion, is saying this holds even after I fix the value of a subset of the variables. Right, so in an actual independent distribution, right, if these were like a product distribution, if I fixed x1 to be 1, the remaining variables would still be independent. We can't hope, of course, that you'll have, fixing x1 will have no effect on the rest of the variables. That would just be the complete graph. But we can hope that even after fixing x1, I'm still sort of pseudo-independent, that I don't start losing structure as I fix variables, that I always remain looking independent no matter how many variables I set. This is really the critical part of being a local spectral expander, is that you act pseudo-independent under restriction. I'll note that there are, of course, other notions of high-dimensional pseudo-randomness, like walks on expanders and things like this. These typically do not satisfy this second property. They will sort of have bounded pairwise or global correlations, but they won't act well under restriction. This is really the piece where high-dimensional expansion shines. And let me just mention that, again, where I'm sort of cheating because this is up to self loops, just like in the graph case. A set of variables x1 through xk is independent, essentially if and only if it's the complete hypergraph, right? If every possible hyperedge exists. So you can think about this again as a way in which high-dimensional expanders are a sparse model for the complete hypergraph, just like expanders were a sparse model for n-choose2 for the complete graph. Okay, the second reason, which is actually why these objects were introduced, is more operational, that it's incredibly tailored to what I've called sort of vaguely throughout, but haven't really defined for you, the local to global method or the local to global paradigm. At a very high level, the idea is roughly as follows. Say there's some quantity or function living on the hyperedges that I want to analyze. Maybe it's the mixing of some walk, like spanning trees. I'm going to do this in this sort of local to global way. Because these links are defined to be conditional expectations, often I can find some way to break the quantity into an expectation over local links. And we'll see this done explicitly for this example of trickle down. Then within each link, I'm a nice local spectral expander. So I apply my local spectral expander locally within these broken down quantities. And then I'll try to lift this back up to a global bound on xk. And we'll see that, of course, things typically go wrong around 2 and 3, and it takes a lot of work to make this actually work. But many of the applications are at a very high level just following this paradigm. Break down locally, analyze the easier local objects, and propagate this back to a global bound on whatever sort of property you're interested in. Mixing time, expansion, I don't know, some property testing things, whatever you're interested in. Okay, that's a bit high level, but we'll see an actual explicit example. Okay, so I want to now move on to the random walk viewpoint of things. But I'll pause briefly in case there are any questions. Since, oh, I'm sorry, I lied. I should show you some examples of high-dimensional expanders before we move on. Sorry. So the first example we should check, of course, is the complete complex. Right? I've said that these are sort of a sparsification or a sparse model for the complete complex, and 2SK better be a very good HDX. And indeed it is. It's a 0 one-sided high-dimensional expander. Why? I sort of already showed this before. All of the links are complete. Right? When we looked at that picture before, the base graph was a complete graph on 4 vertices. The links were complete graphs on 3 vertices. Of course, this generalizes to general k dimensions. All your links are complete, and complete graphs are, of course, essentially perfect spectral expander. So this will give you a 0 HDX. The second example I want to talk about is what I'll write as n to the k. It's really the complete multipartite complex. So the vertices will really be n cross k. So think of sort of k copies of n. And I'll have every possible hyperedge that takes one value in each of these. Right? As a simplicial complex, this is really like I have k coordinates, and then each possible value of 1 through n in the first part of this pair. So this is sort of isomorphic to n to the k. This is just how you write it as a simplicial complex. And I'm emphasizing this because we'll come back to it in about 10 minutes. Okay, these are sort of boring examples, right? These are like really actually independent distributions. They're very dense. What's something a little bit more interesting? Here's something pretty interesting. It turns out spanning trees are a high-dimensional expander. Give me any graph. We'll define a complex whose vertices are the edges of the graph G, and whose top-level faces are collections of n-1 edges that form a spanning tree. When I downward close this, and I look at the whole complex, level I are sort of forests of size I. I'm not going to prove this for you, although I'll sort of mention it running throughout, and Jonathan will talk about it a little bit more in the next talk. This also turns out to be an essentially perfect one-sided high-dimensional expander. Okay, so still this is very dense, right? Usually there are exponentially many spanning trees, so I certainly haven't given you a sparse object that's an HDX. So that's sort of the next question. Just like a graph, the degree of a hypergraph is a very important parameter. This is just the number of hyperedges that any particular vertex sits in, right? For looking at vertex 1, how many hyperedges is it contained in? This is the degree. All the examples I've given so far have had massive degree. It turns out, just like expanders, to use these objects in application, in like complexity style applications, to use them as gadgets, we really want to build families of high-dimensional expanders that have O of 1 degree, not depending on the number, an infinite family of complexes that have only O of 1 hyperedges depending on dimension and expansion, but not on n. And okay, like I said, this is really critical in application because it controls the blow up, the cost of using this object in practice. If I start with sort of a problem over the vertices and I blow it up to a problem on the k-sets, this is exactly how much I pay to do this. So we'd like the sparsest possible hypergraphs that still have strong expansion parameters. Okay, I haven't actually told you, how to construct this sort of thing for graphs, and I'm not going to say that much about it, other than that it turns out that it's sort of easy. It turns out if you take a random regular graph, it expands near perfectly. It's not easy to prove, but it's easy to to find them randomly. Expanders are common objects, and often the interesting thing is how to construct them explicitly. And over the past 30 years, we've developed a lot of machinery building algebraic constructions of expanders and combinatorial constructions of expanders. We understand pretty well at this point how to build these graphs. So the first natural question for HDX would be, what about this first bullet? Can I just take a random sparse hypergraph and hope that it's a high-dimensional expander? Okay. Unfortunately, no. This does not work. It turns out that even very dense complexes are not in general going to be high-dimensional expanders. I'm not going to go deeply into this, but even if I take just a little bit less than n to the k minus 1 total hyperedges, right? N to the k would be complete, so this is only slightly better than complete. There are going to be many, many disconnected links with high probability. So it'll be, not even remotely close to a spectral high-dimensional expander. Thankfully, it turns out that this sort of algebraic method does extend to high dimensions. This was first shown, I guess, in 3 dimensions by Ballantine, and then for general dimensions and expansion parameters by Lee and Lubatzi, Samuels, and Vishne. But for all dimensions and all expansion parameters, it turns out there exists an explicit k-dimensional family of lambda HDX of degree about lambda to the k squared, lambda to the minus k squared. The parameters don't matter that much. Yeah. Yes. So people were interested in generalizing the idea of a Ramanujan graph. And this was well before the idea of local spectral expansion and its applications in theoretical computer science. And people sort of looked at these and realized, these have these nice local properties. We can use them in this local global method to prove interesting things like mixing of random walks and things like this. So it is a little bit strange. This actually does predate the definition of local spectral expansion, which was 2014 and 2013. So about by 10 years. The mathematicians were way ahead of us. Yeah. Oh, sorry. Yeah, it's a good question. Not really. You can maybe do slightly better than half in dimension 3 by picking random points on a sphere and sort of correlating nearby points in some set of dimensions or something like this. But we really don't have a good random model which gives you, even that's like n to the delta degree or something like this. So really the answer is no. It's open whether there is a good random model to produce high-dimensional expanders. It seems like a very hard problem. It's a very interesting problem, but not one that I'm going to talk about. Yeah, so this is fine, right? Oh, this would be a bounded degree graph. This is saying a random. No, right? I'm telling you down here that there are constructions of size n times lambda to the k squared. There are linear size constructions. I mean, this is like a miracle. It's incredible that this is true. But it turns out you can do this. And yes, yeah. And Yotam will talk more about this tomorrow. Okay, let's move on so we can. Oh, sorry.
Of how well you can get this degree for like regular.
No, this is a fantastic open question. Okay, these are called Ramanujan for some different reason. It's not actually sort of corresponding to this degree parameter. I don't know if Yotam will talk about this. I'm happy to talk about it offline. It's an incredibly interesting problem. We don't know optimal trade-offs for these objects. We don't even know if k squared is the right asymptotic dependence in dimension. For instance, this is open. Yeah, there are lots of super interesting questions around here, but because I'm running out of time, I'm going to move on beyond constructions, which will be, there's going to be an hour-long talk on constructions tomorrow. Don't worry about it. Maybe worry about a little, but not right now. Okay, I want to move to random walks. This is really, we've set up a lot of stuff. Let's actually see what you can do with it. Let's look at some of the meat of high-dimensional expanders. So we already briefly mentioned that graph expansion is really inherently tied to G's the underlying random walk or lazy random walk on G, right? It essentially controls the mixing time. And a question which was a natural question that was first considered by Parzanchevsky and Rosenthal, sort of in the topological literature, and more from the modern perspective by Kaufman and Mass. Largely everything we talk about here will be following this work of Kaufman and Mass. Is there some way to extend this connection to high dimensions? Is there some way that spectral expansion of hypergraphs, local spectral expansion, controls the mixing time of some high order analog of the random walk on a graph? Okay, the first question here is, what is the right high order analog? Like what random walk on the complex am I interested in? It's not so obvious, right? How to define a random walk on a simplicial complex. And there are many ways to do it. I'm going to follow this way of Kaufman and Mass that has turned out to be extremely influential after. And to motivate this, I want to start with sort of a simplicial view of just the standard graph random walk. So for now, ignore that like x3 exists on this diagram. Let's think about just the random walk on the one, the base graph of this complex, which was just a copy of K4. So this is just a standard walk procedure, right? Let's say I start at vertex 1, and I look over to its neighbors. I pick a random neighbor, say 4, and I move to it. Over on the simplicial complex, you can sort of view this as the following up-down procedure, right? I start at 1. Who are my neighbors? I look at everything, all the edges above me that I'm connected to, right? I'm connected to 2, 3, and 4. And so I move up to sort of a random edge, 1, 4. And then I'll move back down to one of its endpoints, 1 or 4. In particular here, I picked 4. So this, hopefully you notice, corresponds exactly to the lazy random walk on a graph, right? This procedure, this sort of two-step formal procedure where I have an up step and then a down step on the complex where, I starting at V, I pick a random edge containing V, move from 1 to 1, 4, and then I take a uniform step down. I subsample with half probability 1 with half probability 4. So this is lazy with probability a half, right? There's a half probability I come back to where I started, and otherwise it's the standard random walk. This is exactly the lazy random walk on G. So there's a very natural way to view this as an up-down process on this simplicial complex and on this diagram. Okay, hopefully this suggests a fairly natural generalization to other dimensions. Right? There's no reason that I'm just stuck on walking on x1 in this sort of up-down procedure. In particular, ignore the text for the moment. I can also perfectly well do start at an edge like 1, 4, walk up to a triangle, and then walk back down to another edge. Right? This gives me a series of high-order analogs of the random walk of the base graph. And in general, we can define this at level I. I'll call it the up-down walk, P sort of wedge I. And this is just exactly this procedure that starting at S, it walks up to an I+1 set that contains S, and then it walks down to a random I subset. Or in other words, it removes a random vertex to move back down a level. Okay, the other natural thing I could do is reverse this process. Right? I could instead start at a triangle, first take a down step, remove one thing, and then walk back up to a new triangle. This is called the down-up walk, and I'll denote it by this lower wedge I. So this is basically the sequence of random walks we'll be interested in the complex that generalizes in I think, a very natural way the basic graph random walk. And Jonathan will talk about this more. It was realized by Inari, Liu, Ovescron, and Vincent that this down-up walk is a vast generalization of a well-studied set of Markov chains called Glauber dynamics in TCS and statistical physics. I'm going to show you 3 basic examples, and Jonathan will talk about more applications throughout statistical physics and TCS. Okay, so here's an example. We already saw it. This is exactly the Markov chain that I described to you on spanning trees on slide 2. Right, so if we take the spanning tree complex, we start with a spanning tree that's 3 of the edges of K4. I remove one of the edges at random, this left guy, and then I take the up step, I add it back in, and I get a new spanning tree. So this is exactly the down-up walk on a high-dimensional expander, right? Since we've claimed without proof that the spanning tree complex is an HDX. Okay, so there's example 1. Here's another example that comes from this complete multipartite complex I described before. The hypercube complex. So here, this is basically setting n to be 2, right? There are k parts, each of size 2. The complex formally is I have k coordinates. Each of them has a vi, and they can take all possible Boolean values. What does the down-up walk look like here? Well, I'll pick a random coordinate, vii, and then I'll remove it. When I walk back up, the only thing I can do is replace that coordinate, right? I still have all the other coordinates in my complex. So I'll pick a random vi prime, 0 or 1, and put it back in. Hopefully this is an object you're all very familiar with. This is the hypercube graph, right? This is like the Hamming distance 1 graph. It's the most classical graph or object in TCS. And thankfully, we understand everything about it, right? By basic Fourier analysis, we understand its full spectrum, mixing, et cetera, et cetera. Just the one thing I'm going to point out here is that, maybe you've seen this, maybe you haven't, but lambda 2 of this procedure turns out to be 1 minus 1 over k, coming from sort of the basic characters of the graph. And this hopefully raises sort of a natural question. If in some sense HDX are like this is basically k-independent random variables. We've talked about HDX as being sort of k pseudo-independent random variables. Can we prove that for any strong enough lambda HDX as lambda goes to 0, that the lambda 2 of this down-up walk, and therefore the mixing time, approaches 1 minus 1 over k, to give you polynomial mixing time in dimension? Okay. So I think somewhat amazingly, the answer is yes. This was proved in a series of works. Technically, the way I formulated the question, this was resolved by Kaufman and Oppenheim in 2017. I'm going to show you a very elegant version of this theorem later due to a Lev-Lau that's slightly finer grained, and Jonathan will use it in his talk. That if we define not just a single expansion parameter, but for every level of the complex, we let gamma I be the worst case expansion across links of size I. I fix an I face and I look at that link. The worst expansion is gamma I. Then the lambda 2 of this random walk, the expansion of the down-up walk, is upper bounded by 1 minus 1 over k. times this maybe slightly mysterious product across the spectral, all the local spectral gaps in the complex. So let me just slowly see a couple of examples. First, imagine plugging 0 in there, right? In the spanning tree complex, or in a 0 high-dimensional expander, this product is just the product of 1 with itself, k minus 2 times. So this product completely, right, 1 minus 0 is 1. Hope we all agree. This just becomes 1, and you get 1 minus 1 over k. So indeed, in a 0 HDX and in the spanning tree complex, you will sort of match the eigenvalues of completely independent variables of the Q. And plugging this into our mixing time from before, this immediately implies that this process, this Markov chain that we discussed at the very beginning, you only need to take about n squared, sort of, replace one edge, add it back in steps until you're very, very close to a uniformly random spanning tree. This isn't the best bound you can possibly get. You can use more complicated machinery to get near n log n. But for now, it's fairly amazing, even just using these sort of very local parameters, that you can get a polynomial mixing time. And perhaps more amazing than this is that spanning trees are just really a very special example, right, of the sort of thing that this can handle. It turns out that more generally, a generalization of spanning trees called matroid bases are also 0 local spectral expanders. And this ended up resolving a long-standing open conjecture on the mixing of matroid bases called the Mihail-Vazirani conjecture. I won't go too deeply into it, but it's just to say that this is a very powerful machinery, even though it looks so simple. The other sort of parameter setting I want to mention is you could also imagine these being all about 1 over dimension, being 1 over k, right? And now this product on the right becomes 1 minus 1 over k to the k, roughly, which is a constant, which is O of 1. So if all of my expansion parameters are about 1 over k, then plugging this into the mixing time, I end up getting roughly mixing like k squared log n. So this walk will mix in polynomial time and dimension and logarithmic time in the number of verses. So Jonathan will talk a little bit more about applications like this and sort of various parameter settings of interest. I'm pretty close to out of time, but I want to get to this last question that you asked about, which is, this is a great theorem, but there is a little bit of a problem. In fact, even in our definition of local spectral expansion, which is that it's not really fully local. This theorem and our definition require this bound on the base graph, the expansion of the base graph, which is truly a global quantity, right? Like we said, this is capturing pairwise correlations in X. If you're looking at an object with exponentially many different possible correlations, this could be very, very hard to compute. This leads us to a really beautiful theorem of Isar-Oppenheim, called the trickle-down theorem, which says it turns out up to connectivity, it is sufficient just to bound only the expansion of very top-level lengths in the complex. If I look only at these objects where I fix everything but 2 variables, I just look at these local graphs, it turns out that's sufficient to prove the entire complex is a high-dimensional expander and therefore has fast mixing, etc. So formally, the statement is that for any k-dimensional complex where the k minus 2 lengths have expansion lambda, the base graph, and second, we'll assume connectivity throughout all the lengths, so lambda is less than 1 for all the base graphs. Then we can bound the expansion of every link by lambda over 1 minus k minus 2 times lambda. So there's some slight decay as you trickle down in the parameter, but if lambda is much less than, say, 1 over k, we end up getting good expansion for the base graph. And in particular, if lambda were 0, right, plugging in 0 here, you're still going to get 0. So for proving, for instance, that spanning trees are 0 high-dimensional expanders, all I have to show is that the links are connected and look at the very top-level guys and prove these are like complete multipartite. That's a very simple combinatorial exercise. I'm not going to do it, here online, but it can actually be worth just going through and jotting down why this is true. It's a simple combinatorial proof. Okay. Any questions? I think I was hoping to get to actually giving you a high-level idea of the proof of this, but maybe I'll just flash a, yeah, good.
Then every link has a base graph that is a lambda.
Yes. Yeah, so actually, just very briefly, let's just look at the case k equals 3. What does this say? It says, I'm promised that the base graph is connected, and I'm promised that every link, so I fix a vertex and I look at the local graph, I'm promised this has expansion lambda. We want to show that you get this slight decay, that the base graph actually has expansion lambda at least, or at worst, lambda over 1 minus lambda, right? So in particular, if lambda is strictly less than a half, in this case, we're going to get some non-trivial expansion of the base graph. I think I'm basically out of time. I was going to sort of show you how this proof works. Instead, I'll maybe just briefly flash the idea, which is called Garland's lemma, and is basically an instantiation of this local to global method that I mentioned before. Roughly speaking, to bound lambda 2, what we're interested in is bounding this, what people call the Rayleigh quotient, right? This is standard spectral graph theory. And the idea is just what I said before, that we'll basically break these global quantities into an expectation over their local variance. So we'll write, this global inner product as the expectation over links of the local, basically the local Rayleigh quotient, the local inner product of the adjacency matrix of V and the local functions FV sitting on the links. I won't define this for you, but yada, 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 yada. Roughly speaking, we have this global quantity, this inner product we want to bound. We break it into the local quantity. Now we try to use local expansion to pull out this lambda factor, and then we lift back to a global bound. What I've done here is lie horribly for various reasons. Really, because this inner function here might not be orthogonal to 1, and really the interesting part of the proof is sort of handling this fact by looking at the perpendicular and parallel parts. It's not too important. Well, it is important, but I'm out of time. So, if you want to see this, there are many excellent lecture notes online that cover this proof and the ideas in it. But I'm out of time. I want to keep a few minutes for questions before we move on. So I'll throw up a conclusion slide and just go to the questions directly. So thanks so much, everyone.